And while we're at it, we are going to actually talk about a subfield test too. Remember that a ring differs from a field in only two axioms. Okay, so there's only two more things that we need to check to make a ring a field, right? Or to see if a ring is a field. So there was a subring test, so likely there's an analogous subfield test, and I should have brought this up when we were talking about fields, but I think it's better late than never, and I think now is a good time that we've talked about subrings. So suppose F is a field. Let F be a field. And actually, I should be a little bit more careful. Let's say F with some notion of plus and dot is a field. So we have a commutative addition, commutative multiplication, and every non-zero element has a multiplicative inverse. Let F be a field. Suppose K is a subset of F such that 1, there's two ways of writing this. There is K has at least 2 elements, and or we can just explicitly say it. So there's multiple ways of doing the subfield test. I'm going to decide that we want, this is the additive and multiplicative identity. 0f and 1f should be in K. Another way of saying this is K has at least 2 elements. It's equivalent in terms of how you actually apply this test, but it's no harm in saying that these are the 2 elements that it has at least. It's closed under subtraction. Let me put it this way. K is closed under subtraction. And K is closed under division by non-zero elements. I.e., let me just clarify this one because it's slightly different than the subring test. For all A, B, and K, with B not 0, A times the multiplicative inverse of B, which is A over B, is also in K. Okay, so proof. Let's write it like this. We want to be in a situation where we can use the subring test. And the criteria for the subring test is that you have 0, you're closed under subtraction, and you're closed under multiplication. We're not closed under multiplication, at least we don't know we are yet. So let's first show that that K is closed under multiplication. Okay, so how are we going to do that? Well, pick any B not 0 in K. Then 3 and 1 tell us that if we take 1 and we divide by B, which is 1 times B inverse, that's the definition of division, you multiply by the inverse, that's in K. Because 1 is in K and B is in K, so I can divide 1 by B. Thus K is closed under multiplicative inverses. Great. And we're going to do now the same trick we did when we did the subring test. So if A is any other element, then A divided by B inverse is also in K. Let me scroll down a little bit here. That's also in K, but A divided by B inverse is, by definition of division, A times B inverse inverse, but the inverse inverse is just AB. So K is closed under multiplication. Okay, so now we know that K is closed under multiplication. So by the subring test, because F is a field, in particular, it's a ring. K is a subring of F. Why? Well, K has 1, K is closed under subtraction, K is closed under division by non-zero elements. Fantastic. This means we only need to check 2 things. We need to check that multiplication in K is commutative, and well, we already checked that it was closed under multiplicative inverses. So actually, we just need to check that it's commutative. That's the only extra bit of detail that makes a subring a subfield, namely closed under multiplicative inverses and commutative multiplication. But, so that this is the only thing that's left, but multiplication in F is commutative, so it must also be commutative in K, because K is less elements. So I know that original subring test was quite long, but we were able to get rid of, I don't know, more than half the checks for the field checks, the field axiom checks, by just applying the subring test, right? We don't have to check distributive property, we can just apply the subring test. We don't have to check any of the additive properties, we can just apply the subring test. The only thing that we really needed to check was closure under multiplicative inverses, which we did up here, and then multiplication being commutative, but it's commutative in F, so that was here. And that's really all the additional things we need to check when we have a field. So this is sometimes called the subfield test. And just to give you one more piece here, usually if K is a subfield, well, let me write it like this. So suppose K is a subset of F, and K and F are fields, where the plus and dot in K comes from that in F. Comes from the plus and dot in F. Then we say exactly what this test is saying, namely K is a subfield of F, and or F is an extension of K. And usually we have special notation for this. So we write F over K, like that, where it doesn't really make sense to divide them because they're fields, they're full-on sets, but nevertheless, we have notation for it. And then the last thing I'll do here is just give you an example. R is a subfield of C. We don't need to go through the test, but you can if you like. In fact, Q is a subfield of R, and R is a subfield of C. Oops, subfield of. So Q is a subfield of both R and C. And there's lots of other interesting fields that are subfields of R and C, but these are just some examples using this notation. And similarly, we can write that C is an extension of R. It's actually a very nice extension of R. If you take Galois theory, you'll learn about field extensions. And R is an extension of Q. This is actually a very nasty extension. This one's actually very nice. And this one's kind of nasty. And if you want to learn more, we won't really cover extensions so much in this class. This is the domain of 6016, which is our graduate algebra course. Okay,